Hi! Within this section, we're gonna focus about the physics terms and physics concepts that we should learn in order to understand the quantum computers better, and then we will dive into the qubits, okay, quantum bits. So as I said before, I'm not a physicist, okay, I'm not a quantum physicist, I'm a software engineer. However, we need to learn about this stuff. At least we need to learn about the basics of this stuff. We need to understand the terms, understand the concepts, so that we can actually learn about qubits and quantum computers. There is no way for us to proceed without learning about this stuff. Obviously, you can actually go into the YouTube or any other channel or any other source in order to deep dive into this physics concepts. But this is not what we are doing over here. As I said before, this is not a quantum physics course, this is quantum computing course. But we should understand some terms and concepts in order to proceed. Now what we're gonna do, we're gonna be focusing on something called double slit experiment or Young experiment. Young being the physicist who has actually conducted this experiment, I believe like 150 years ago. Okay, so this is not about quantum computing or some recent development. This has been there like for many ages. So what we're dealing over here is like a light source, okay? And the Young actually conducted this experiment with a candle light. So you're seeing like a laser light over here. Of course, you can do this with a laser. It will be much more, I believe, appropriate for this kind of experiment. But back in those days, they didn't have lasers, so they just went with the candles. So why we're dealing with light? So light has the photons, okay, as the tiny structures. So these photons make up light. Like we're gonna be dealing with that kind of subatomic particles when we're dealing with quantum physics. Because quantum physics is actually the part of the physics or like the subsection of the physics that is interested in very small particles or very cold particles, so very isolated particles. So what we see in the quantum physics is not very relevant to the real world physics, okay? They are completely different because we are dealing with very small stuff, okay, subatomic particles like electrons, for example. And photons actually behave the same, so we can just do this with photons or maybe electrons. So what happens over here is actually we have a double slit, okay, or we have like a card that has nothing inside of it, okay? Just consider a card without any slit. If you just give a light to that card, it doesn't actually go beyond that card. So you don't see any light on that white board over there. But if you have one slit, of course light will get through it, right? And you will only see like a one shade of, like a one ray of light just reflected on that whiteboard if you have only one slit. But if you have a double slit, then you have this pattern over here, which actually doesn't make sense when you first look at it, because if you have only one slit, then you have only one ray of light concentrating on one part over there. But if you have double slit, then you have like 5 or 6 or like multiple ray of lights over there, like concentrating in some weird pattern, right? And you don't see the light between these patterns, so it's very weird. But you should also know that there was an ongoing debate about whether light is a wave or a particle. So photons behave like a particle or they behave like a wave. Because if they behave like a wave, then this interference pattern that we see over there actually makes sense. Okay, but if they behave like a particle, it doesn't make sense, because if you have double slit, if you have two slits, then they have to go through that slits, and they should just have two lights over there, right? But we have this pattern over here appearing. So immediately you can think that, yeah, so light is a wave. And it doesn't make sense to think otherwise, right? So yep, that was the initial thought. And it happens that this is not completely true. So first of all, we need to understand, if we assume if light is a wave, then why do we have this interference pattern? Why am I saying that, yep, then it's regular to have this interference pattern? Maybe you don't understand this, but there is a very simple explanation for that. So let me show you with an animation over here. If light is a wave, then it actually, as you can see, they go through those slits, and if it's a wave, then it actually interferes with each other, right? So you have light waves coming from one slit, and you have light waves coming from the other slit, and you're just actually seeing that they are interfering with each other. And when they interfere, if they interfere in a way that they actually support each other, then we call this constructive interference. But it can be in a way that they actually collide, in a way they distract each other. So it makes sense. We see the constructive interference in a way that they concentrate around this blocks, and they actually create this interference pattern. That's why we don't see some light between those ray of lights, and we see only shade, because there are some deconstructive interference as well. So it makes sense, okay? If that was the case, then actually this wasn't some kind of an interesting approach, okay? So there isn't anything funny about it. But it doesn't stop there, obviously, because there will be always some weird things happening inside of quantum world. So we see this interference pattern, but there is some weird thing going on. So physicists thought that, yeah, maybe these particles, these photons going through one slit, and some particles going through other slit, and since this is a wave, they are colliding with each other, and it's forming the interference pattern. But what happens if we try to see what kind of slit they are going through? Okay, for example, if one particular photon going through slit 1 or slit 2. So they introduced some kind of measuring, okay? So for example, if a photon going through this, then they would know. If a particle going through this, then they would know, and they could understand this in a much better way. So they introduced some kind of measuring system, like an alarm or alert system. They put some kind of observer into they introduced some kind of observer to this experiment. And what happened over here is that the weird part over here, when they introduced this observer, they saw that they lost the interference pattern. They only saw two rays of light appearing at the center of the whiteboard over there, as if the photons are just going to the slits directly, and they are behaving like a particle. So that was shocking, because how would photons know that they're being observed, right? So it doesn't make sense. You expect them to just create this interference pattern over here, but if you observe it, then they don't create that pattern. So this is very weird. And they just took it one step ahead. So they said that, what happens if we don't observe, okay? and but we just actually leave the observer device over there. Okay, we leave the device over there, but we just plug it out of the electricity, and let's see what happens. And as if the photons would know, the interference pattern emerges again. So when they're observing, it actually collapses the wave function. Okay, so we're gonna just use this term a lot. It actually collapses the wave function when we do a measurement in this experiment, and we don't see this interference pattern. So this is shocking again. Another shocking thing over here is that, okay, they lose the observation, okay, they just get rid of the device, and they say that what happens if we just send photons one by one? Okay, not as like a light source or like a candle, but one by one photon at a time. And just have a device of the other side, like the whiteboard. So when a photon hits on that whiteboard, it just marks it, okay? So that we would know where those photons landed. So guess what happened? Even though they send these photons one by one, the interference pattern emerged again. So how would this happen, right? Because it's only one photon. What kind of thing it's interfering with? So it's unbelievable, right? So what happens over here is that only logical explanation is that that photon itself is interfering with itself. Okay? So that photon is in a way that it's in a superposition. It's in the left slit and it's in the right slit at the same time. When we observe this, we break this superposition. Okay? So superposition doesn't mean that we have multiple photons. Okay, doesn't mean that it's over there and over there and over there, but it's actually the possibilities of being everywhere when we don't observe it. But at the time it actually reaches the destination, it goes around somewhere, it lands somewhere, and it creates this interference pattern again. So this is what superposition means, and this is what interference means. So remember, we have three principles that we mainly focus on quantum computation. First of which being the superposition. Okay, so qubit can have 1 and 0 and anything in between, and they can actually have it at the same time. But it's actually not having the value same time, it's having that possibility at the same time. Okay, so over here we see that even a single photon can be at the left hand side or around the right hand side. It can interfere with itself and can land anywhere on the other side of the whiteboard. And interference is that they actually collide with each other, and they just have a constructive interference or deconstructive interference, and they land somewhere in the whiteboard and just create that interference pattern. So you have to be careful over here. You need to remember the collapse of the wave function. Okay, you need to remember about superposition. You need to remember about interference as well. So maybe you don't understand why this happens, okay? Why this happens, why there is something called superposition. Do you see a superposition inside of the world in like real life? You don't see it, right? But we are too big to understand this. Again, this is happening inside of the atom, or this is happening like in a very small scale. There is a saying that we're not actually, the quantum physics is not actually very weird. We are just too big. And as the Richard Feynman said, the famous physicist said, if you think that you understood the quantum physics, then you didn't understand anything about the quantum physics. Okay, so maybe you're not actually understanding why this happens, okay, but this phenomenon exists, and we can use these photons, or we can use this some same kind of atomic particles as qubits in order to leverage this quantum mechanics in order to have much more capability in the computation power. We have to learn about entanglement in order to understand this in a better way, and we're gonna do that within the next lecture together.